So it's interesting. Some people were doing head-to-head comparisons. So they take the little custom code sets. This was a group that actually did this work independently. I'll describe this in detail. But what we have is we're going to have breast cancer samples actually examined and analyzed using the Xenium from 10X system on their breast cancer panel. It's a 280-plex panel just for breast cancer. And I'm going to compare that, or it's going to get compared directly with a CosMx 1000-plex. That's a generalized panel that should work on any kind of organ type, and it does. And we're just going to look at what are the results if you take the same sample and run them back to back. Now, this is work done at the University of Tokyo by Yutaka Suzuki. The data is part of the public domain. So we made it out there, so you don't have to believe me. You can go out there and examine this with your own data. And I'm just going to give you an idea of what you see when you go in and look at that data. You can see the URL down there on the lower left, so you can examine this yourself. So when Yutaka made that measurements, this is what he finds. I have 1,000 genes. The Xenium has 280. And if you look at the mean transcripts per cell that you examine, you do the measurement with the CosMx, you're measuring about 554 transcripts per each cell. And on the Xenium, you're getting about 116. So that ratio is about 5 times more transcripts, higher sensitivity in the CosMx for the Xenium. And if you actually get rid of the segmentation thing, just look at transcripts per square micron, it's about 10 times the number of transcripts per square micron on these samples. And if you look at genomic breadth, how much biology I'm measuring, I'm seeing 163 unique genes, and the Xenium is seeing about 43. So that's what you'll see in a head-to-head comparison. Now, if you look at each individual gene in correlation, this is what you'll see here. You also get a sort of independent measurement of the sensitivity ratios. The sensitivity ratios just show up as the slopes. So SMI is on X and the Xenium is along the Y. You'll see that we're a little bit more sensitive. When you're in a tumor bed, we're a little bit more sensitive than the Xenium technology. Cell sizes we get are identical. And then we go into the area of more complex tissue geometry. These are the stromal regions. And the stromal regions are a little bit different. You can see the whole graph looks a little different. And it looks like, well, okay, maybe Xenium's a little more sensitive in the stroma. But then when you actually look at the data, you got to say, okay, what are the cell sizes in the Xenium versus the cell sizes in CosMx? CosMx is seeing a much smaller cell size than the Xenium. The Xenium's got really very large cells. So maybe that's the reason why they got more transcripts in there. Question is that real? Are those cell sizes real? And I'll come back to that in a slide or two. This is why we spend a lot of time on cell segmentation. This is how our cell segmentation works. High-plex proteins lighting up the plasma membranes. We have an AI ML driven engine, artificial intelligence machine learning engine called CellPose that's driven under there. And then we supercharge it by combining it in unique ways with unique logic to actually figure out what cell sizes we're measuring. So that area where you saw the difference in sensitivity, this is what the area looks like segmentation-wise. This is why the Xenium has these very large cell sizes here, and it's sort of like the extra transcripts are sort of, artifactual in a sense. They don't belong to individual cells. They belong to combinations of cells. There's the segmenting on the CosMx. You can actually measure the cell sizes, and we did that. There's the CosMx cell sizes. These are the expected ranges. This is what you get. These are the cell sizes that come directly out of the Xenium analysis. And you can see here, here's the normal ones. And these are all these sort of, I call them sort of cell mixtures. These are boundaries where multiple cells are actually put together and the data all comes together. Increases the transcripts, but you're losing the pure single cell of spatial single cell because you're getting doublets, triplets, quads, all mixed together in your cell counts. And when you do the cell typing, this is what you see. We actually took that data. We're not doing our cell typing. We got a great cell typer. So let's just take the raw data, Xenium, CosMx, toss it into Seurat, which is a public domain program, and just let Seurat cell type these two things and see what they get. And what you see, and I tried to highlight that, it's sort of unusual if you haven't looked at these things a long time. What you're trying to look for is cell types that have a unique pattern that doesn't correlate with all these other cell types that are nearby. The tumor correlates with itself, so that's where you see here and there. But these other areas where you don't want to see a whole big blob where all the cells are sort of mixed together. And that's what you see. You see places over here where the cancer-associated fibroblasts, vascular cells, poorly differentiated from each other, T cells and myeloid lineage classes that actually are cross-talking that actually shouldn't. Whereas on the CosMx side, you get pure cell types because that segmentation worked and you get the RNAs in the right positions. So it's an important thing to remember. Yeah, you got to look beyond like things like false positives. These are not dominant terms in these types of technologies. The cell segmentation errors are.